Hello and welcome to MATLAB Programming for Numerical Computations. We are in the first part of Module 3. In this part, we are considering numerical differentiation. In the first two lectures, we considered numerical differentiation in single variable. We looked at obtaining df by dx and d square f by dx squared using forward, backward and central difference formula. In today's lecture, we are going to extend that idea to finding partial derivatives. Partial derivatives when the function f is a function of multiple variables. So f is a function of x1, x2 and so on. Before we do that, we will go over the example that we took in the previous lecture, the practical example of rate of reaction. We wanted to find its derivative with respect to temperature T at T equal to 600. We use the central difference formula with h equal to 10 to the power minus 4. At the end of this lecture, I had suggested that as a practice, what you could do is you could try to solve this problem for various different values of h. In today's lecture, we will spend a few minutes trying to look back at that same example, modifying the examples to choose different values of h and obtain what is the optimum value of h that we need to use. We are not going to look into the theory behind it. We are interested in practical aspects of how we will apply this theory in order to solve problems using MATLAB. In order to do that, I'm going to give you a certain set of tips. What we will find is that the judicious way of choosing h for central difference formula is to choose h as temperature T multiplied by 10 to the power minus 6. If we were using forward or backward difference formulae, then the optimal value of h would be T multiplied by 10 to the power minus 8. Where does this come from? This comes from the fact that the optimal value of h is proportional to the machine precision to the power 1 by 3. The temperature is not of an order 1 but is of order 100. We need to proportionately increase h as well. Okay, so this is the practical tip that we are going to use, and we will see how this problem works out by going to MATLAB and trying to solve this problem. So let's head on over to MATLAB. Okay, so this was the code that we used in the previous lecture. What I'm going to do is now modify the code for different values of h. The different values of h that I'm going to take are as follows. 1e minus 3 to 1e minus 7. I'm going to multiply this with t. Okay, so the value of the independent variable temperature at which we want to find out the first derivative, that's the value that we are going to multiply our h with. Okay, now because now our step sizes is a vector, we have seen this in the previous lecture, what we need to do in order to obtain all these results at one go. What we need to do is we need to replace the slash with dot slash. Okay, this guy is a scalar. So scalar, when we want to divide that by a vector, we need a dot slash. So in the parenthesis, what we get is going to be a vector. So the thing that I have highlighted is a vector. exp function exp works on a vector as well, and it's element by element exponent of that vector. So this is also going to give us a 1 by 5 vector. We are doing scalar multiplication with k and c, so we don't need to change these star to dot star at all. Okay, same changes we need to make in this expression as well. We change the slash to dot slash and no other difference, no other change we need to make at all. And finally, numval, the numerator is a vector, the denominator is also a vector, so we need an element by element division, and we obtain that by a dot slash over here. None of the other things need to be changed. Okay, so let me save this and run this. And let's see after running what are the various errors that we get for the various values of h. So when we run this, I'm displaying the various errors. We see that the best case errors are over here. Okay, for these two values of h, we have the best case errors. If I type out h, what I get is that I get best case errors for 6 into 10 to the power minus 3 and 6 into 10 to the power minus 4. So h, we do not choose it blindly, but we need to choose our optimal h as machine precision to the power 1 by 3 multiplied by the absolute value of the independent variable of interest. The take home message is that there is an optimal value of h for which the central difference or the forward difference formula gives us the best results. So now let us go on to this particular lecture. In this particular lecture, we want to find out df by dx when f is a function of multiple variables. As a matter of fact, we have done this already in the previous example. In previous example, if you think about it, the rate expression is a function of both temperature and concentration. So what we had done in this particular MATLAB code was this, is we held the concentration value constant at 1.0 and varied the temperature to T plus H, T minus H, and found the central derivative. So that is what the definition of partial differentiation is. Partial differentiation means dou f by dou x1 keeping x2, x3 and so on constant, dou f by dou x2 keeping x1, x3, x4 so on constant, and so on and so forth. Okay, so that is the definition of partial derivatives. In order to calculate dou f by dou x1, we hold x2 constant and vary our x1. In order to calculate dou f by dou x2, we hold our x1 constant and vary our x2. You will notice that a partial differentiation is kind of like finding the gradient of a scalar. The gradient of the scalar is nothing but dou f by dou x1 and dou f by dou x2 written as a row vector. Let's go to MATLAB and solve this problem for finding partial derivatives. Okay, so our a, the value of x at which we want to find dou f by dou x. So we want to find dou f by dou x at x equal to a. A is going to be a vector. Let's say we wanted to find this at 0.5 and 1. So our a is 0.5 and 1. Our true val or our h step size should also be a two value vector, 1e minus 6 and 1e minus 6 as well. Okay, so true val cos x1 multiplied by e to the power minus x2. So cos a1 multiplied by exp minus a2 and the second guy is minus sine x1 e to the power minus x2 minus sine a1 multiplied by exp minus a2. Okay, partial derivative with respect to first variable. Okay, we will choose our x is going to be equal to a and x1 is going to be equal to a1 plus h1. Okay, now our f1 is going to be equal to sine of x1 multiplied by exp of minus x2. Okay, so this one is at x1 plus h and x2. Likewise, we need to calculate our f2 at x1 minus h and x2. So let's copy and paste this. X1 equal to a minus h and f2 is sine of x1 minus e to the power minus x2, and our numDiff1 is going to be nothing but f2 f1 minus f2 divided by 2h by the central difference formula. Then we copy paste this and say that we want to find partial derivative with respect to second variable. Is this function f of x, rather than we give this function in this particular form, it's recommended that we give we have a separate function file where we define sin x1 and e to the power minus x2 as that function. So for the second partial derivative, the second variable, that's what I'm going to do. So I'm going to create a function fval equal to my fun m3, my fun for module 3, and my input argument is x. Now x is a vector. X are not two values, these are not two variables, but x is a single variable, okay, and it's a vector variable. And what I need to do is we need to write fval is going to be nothing but sine of x1 multiplied by exp of minus x2, semicolon, end, and save this as my fun m3. Okay, what we want to do over here is we will do it in a slightly different way. What we will do is we will define our h temp underscore h equal to 0 h2. Okay, this is a better way of doing things, because when we do x plus temp h, the first guy is going to be just x1, the second guy is going to be x2 plus h2. Okay, our f1 is going to be nothing but our my fun m3 computed at x1 comma x2 plus h, which is nothing but a plus temp h. Okay, and our f2 is nothing but my fun m3 a minus temp h, and we will have num def 2 as f1 minus f2 divided by 2 multiplied by h2. Okay, and the same thing that we need to do over here, this also should be 2 multiplied by h1. Okay, so this is the partial derivatives. Let's display results. So the first thing we want to display is error equal to abs of trueval minus num diff. So let's save this and let's run this. Clear all, CLC, partial differentiation. Let's hope that this runs without an error. Okay, so this is the result. If you see this particular guy, the difference between trueval and num diff turns out to be of the order of 10 to the power minus 11, and the numerical derivative is 0.32 and minus 0.17. Okay, so this is how we take the partial derivatives. Okay, now let us move on to, so we'll take the same example for rate of reaction, where k as before was 1000, E by R was 2500, and we need to find dou R by dou T and dou R by dou C at T equal to 600 and C equal to 1. That is what we need to do over here. What I would recommend you do is you can pause this video for a short period. You can go on to MATLAB and you have this MATLAB code over here. What I recommend you do is you can take this particular part of that code and try to modify it to solve this problem. Okay. Okay. So what I will do is create a new script. We'll copy this. partial differentiation. Okay, so our h value is going to be 1e minus 6 multiplied by t, and the other guy is going to be 1e minus 6. That's going to be our h values. Okay, numDiff1 is going to be my rate x1 minus my rate x2 divided by, let me call this as h1. And numDiff2, I'll call this as also the same but divided by h2. Divided by h2. Okay, so what exactly am I doing over here? Well, let me just first save this. Reaction partial diff is the name of this script, and the name of that function is r equal to function r equal to my rate x. Okay, t equal to x1, c equal to x2, and as we had over here, our r is this guy. Let's go over here and remove this from here and move this to this file. Constants, current value of t and c, rate calculation. Okay, I will save this as my rate. Okay, so when I call this my rate with x1, what it should give me? What it should give me is r calculated at t plus h and c. When I use this at x2, it should give me r calculated at t minus h and c. Okay, so that's what I will do. x1 is going to be equal to t plus h1 and c. Okay, c is going to be kept constant over here. So t minus h1 and c. Okay, so as you can see, the value of c is kept constant over here, and value of t becomes t plus h and t minus h. That goes in the numerator, divided by 2 multiplied by h should go in the denominator over here. Okay, likewise what we do over here is x1 equal to t, the t remains constant at our original value, and c plus h2, and x2 is nothing but t and c minus h2. Okay, and this becomes numDiff. Display results. Partial derivative, num2 str, numDiff. Okay, let's save this and let's run this. Okay, and when we have run this, the partial derivatives of r was 0.1077 and with respect to temperature, and with respect to concentration it is 38.76. So these are the partial derivatives of R with respect to T and C. With that, I come to the end of this lecture, and this also concludes numerical derivative parts of this module. In the next lecture of this module, I will start with numerical integration, and see you in the next lecture. Thanks and bye.